Hello everyone, welcome to Stardust Discovery.
Hi. Yeah, so today we'll be looking at mastering West African School Certificate Examination physics subject. But today we'll be looking at it in a different way. So the last time we looked at common mistakes with physics theory questions. But today we'll be looking at common mistakes with physics practical questions. So for us to do this, I would like us to consider an exam question. This was June 2021. It was actually a practical question on mechanics. So I have the full questions, to try to screen grab it. But is really about simple harmonic motion. So you're supposed to suspend a ruler with two threads, and of course there will be fixed position at both ends, and then you make the ruler to oscillate when you have a mass around the center of gravity C of the ruler. So you definitely need a timer, like a stopwatch to time the oscillation. So this is an example of a simple harmonic oscillation. So the experiment says that you should, just reading from what we see here, you should determine the center of gravity. So normally center of gravity is supposed to be close to the midpoint of the calibration. So for a meter rule, which is usually a 1 meter rule, that's 100 centimeter ruler, the midpoint of that, which would be around 50 cm, is usually your center of gravity. So you're meant to determine that anyway by putting the ruler on top of an inverted stand or pivot. So you balance that ruler until it's able to stay without support. So whatever position that ruler balances without support, that is your center of gravity. So that's how you find it, normally. Then you should record that. Now, these are little pieces that is easy to forget. So you must make sure that you don't miss out on the little details. So you measure your center of gravity with units. So when I say 50 cm, so you need to put that with the appropriate error, that is rather the appropriate decimal places associated with that measurement. So every measurement has an appropriate measurement error uncertainty. So it comes in form of decimal places. For example, a meter rule, has 2 decimal places. That's how you can quantify the errors in a meter rule. If you are measuring the mass, it takes 1 decimal places. Some of these, you are supposed to know. For the fundamental quantity, there are decimal places that is associated with every quantity. Now, this is different for derived quantities, because once you have done further calculation to estimate the quantity, that has become a derived quantity. So for those ones, you have a general rule of thumb to put everything in 3 decimal places, sometimes 2. So you record that center of gravity. Then the other question, it says read and record the mass of the meter rule. So what this means is that the mass of the meter rule will be provided. So that will be one of the information on the ruler. So you should record what mass is on your ruler. Now that should be with the units, of course. All right. Now they give you the detail of the experiment. Suspend the meter rule by the means of 2 parallel threads of equal length. So I've explained all of that. I'll not go into the detail. But the point is, do this experiment, record the time. For every mass you change, there will be different times of oscillation. So you should produce a table when you do that. So now, let's assume you've done this experiment, you've recorded everything, and you have your tables. Now, let's look at this table carefully. The table has mass, so you are changing mass as you are recording the different times of oscillation, which is your T. So this table as is okay. You recorded your mass, you put it there with the unit, you recorded the time of oscillation, you put it with the unit, and I also see the accurate decimal places given for the mass. However, do you notice that for the time, there are two different, so you have two decimal places here and have one here. Now that's inconsistent. You need to be consistent for whatever you are doing here. So for time, you need to have two decimal places all through. Okay. So you also have water derived units and quantities measured here. So for this experiment, you are asked to find the period. Now the period of the oscillation will be determined by the time of oscillation divided by the number of oscillations. In this case, you were asked to count 20 before you record, and that 20 is your number of oscillation, right? So the time divided by 20 will give you your period. And it's still time, so the unit will still be second, but this is now in the right quantity. So the decimal places needed is 3. So you see that everything here is in 3 decimal places, so which is good. You also have to square that value. So you provide that in the table, the square of the period with the units. Then there is t raised to the power minus 2. You also provide that value with the units. Now, I want you to take note that the time that was recorded here is just 1. However, one of the good practices for experiments like this is to do it more than once and find average. So you will have a better result, and also you have more math when you do that on counting 2 times. So you count 1, T1, count 2, T2, then find the average, so that what you are using to get your period is the average, and have all of that in a table. So that automatically gives you an additional mark. Now, it's also important to remember that when you're counting, you start from 0. You don't start from 1. Now, it's easy to make that mistake. Remember, we are discussing common mistakes. So you must avoid starting from 1. When you start from 1, you miss 1 more count. So all your counting should start from 0. 0, 1, 2, 3, 4, all the way to 20 when calculating or counting your oscillations. Okay, so that's it for the table. This table alone has full mark that is up to 5, depending on the year, but every single detail matters. So your units must be complete and correct. The decimal places must be complete and correct. All right, for you to get your points. Now, thinking about the graph. So when you have this table, what's next? You want to make your graph. Now, what do you need to make your graph? For you to represent the table information into the graph, you need to think about something called scale. So you have to scale up your graph to represent this information. Now you have to decide how to do that. For you to get to the scale, it's important to think of what should be your y-axis and what should be your x-axis. And that brings us to the title. So what the title tells you is what your y will be and what your x will be. So when you hear a graph of t raised to power minus 2, that means that's your y-axis. So your y-axis is t raised to power minus 2 and your x-axis is mass. So a graph of t raised to power minus 2 against mass, that automatically tells you your y and the x. So for every of these experiments, the examiner is looking for your title. So you have 1 marks for title, well written with proper units. If the units are not correct or they are missing, you lose half a mark. Now your scale also is important because that's what will determine how you represent this. So here I'm showing an example. Let's say you look at your x-axis, which is your mass. Now look at what is your mass. Now the set of values or the range of values you have will tell you what kind of scale would make sense. Okay, so here you see 20, 30, 50, 70, 100. Now these are not evenly distributed. So you think about how to represent this. Now your graph, as I'm showing on the screen, they are usually into small chunks, which are usually 1 centimeter wide. So if you choose, to represent for every 1 centimeter wide in x-axis, that you should call that your 10 gram of mass. That means for every 2 centimeter wide, you will have your 20 gram. Now, if this is what you want to do, that means that for your x-axis, you are saying let 1 cm be 10 gram or 10 units. So that's what you're saying. We can do this. The truth is try and error. When you try it and you notice that it's not working, you can decide to change your mind and get a new scale. So you must not follow what the first one all the way down. If you try it and it's not working, you try again. So now let's see, this is for x. Now how about the y? So for y-axis here, which is t to the power minus 2, you see all of these values ranging from 0.2 to 0.4. Now I always look for the highest and the lowest value. So when you look at the range, it tells you, how much space you need to represent that. So 0.2 to 0.4 is small. If you do 1 centimeter to, let's say, 0.1 unit, that means within the first 4 gap, you should have all your points located there. Now this is fine, it's correct, but with what we do in physics, it will not allow you to see your points spread out. First of all, it means all your points will be constrained to that small location. But if you choose a scale that will allow your point to spread out, then you will be able to obtain what is called the slope better. We get to that. Now, I have written down, 1 cm to 0.1 units. I can choose to write, represent my points that way. In fact, I think that's what I ended up doing. If you look at this plot, so you see 0.1, 0.2, right? All the way. Now, everything I need will not be more than 0.4. It's just from 0.2 to 0.4. So I have this tiny spread. Okay. Now, like I said, this may not be a good representation. So maybe we should increase our scaling. So instead of 1 cm to represent 0.2 and 0.1, we can decide to say 1 cm represents, or rather 2 cm represents 0.1. That way we can spread out a little bit. Okay. And another point that you must note is the labeling of your axis. So right now I have this separate arrow showing the direction of this axis, which is my y-axis. But for this experiment, it's actually t1 minus 2 axis. So you label your axis properly, with the proper units for y and for x. Okay, see where I have written mine. But you can choose not to do it this way. You can choose to put your arrow here right away and here right away, and not have to write this separate one. But whichever one, you must define what that axis represents. That's 1 point. All of this we have its own mark. The labeling of the axis have its own mark, each of them. Then the proper representation of or calibration of your graph also have its mark. So here you have 1 cm to 10 units, right? And there is a 0 origin here for the x-axis, and also a 0 origin for the y-axis. Now this is another point that is useful. You want your points to start from origin, or your graphs to start from origin. There are a few occasions where you may not. For example, if I am struggling to fit my points, I could decide that instead of starting from origin here, I break it up. So if you're not going to start from origin, you have to indicate by breaking up, this region, so that it shows that it doesn't mean that everything going forward is from origin. Now, you also need to include negative values. So when you plot your graph, there is always the left-hand side and right-hand side. It's good to include some values over the other side of the negative, both for the y and for the x, because sometimes you could have an intercept cutting through those axes. Okay, and even the way you choose or where to place your y-axis and x-axis depends on the graph. So if you have some negative values on your table, that means you need to accommodate them. So that will determine where on the graph you should put your y and where on the graph you should put your x. Okay. So at the end of the day, you want to, have your point spread out properly. At least 2/3 of your graph should be covered. If your points, aren't covering 2/3 of your graph, actually you lose mark. You lose mark, in the grading. So you need to take note of this. From what I've said now, this y-axis scaling is not going to work. So feel free to change that. That's the whole point of this. I'm not giving you everything correct, but it's good we understand why it's not correct. That's why, I had to put you through that. So you space this out. Maybe you can do 1 cm to 0. Or rather 2 cm to 0.2. Or if you want to remain, or rather keep doing 1 cm to 0.1, it will not work. So you need like 2 cm to 0.1, or go to bigger scale, but whatever it is that will just expand those points. Otherwise, they will all feel crunch. You can even do 0.01, okay, and then scale it up that way. All right. Now, when you plot your graph, let's assume you've plotted your points. In this case, I think you have only 5 points, so it's not gonna be a lot like what you're having here. Now, the plot can decide to be this way, like everything going up, while it's also possible for it to go down or scatter this way. The truth is, for these physics experiments, you won't get a plot that is scattered this way. If you see your plots all scattered like this, then something is wrong with the experiment. So you should have either a positive correlation or a negative correlation. Now, this is the same thing as slope. So when you have your points distributed this way, remember that your straight line must not it must not go through all the points, but at least you should find a balance through all of the points. So just like you can see on this plot, it's not going through all the points, but it's going through the middle of everything. That's what you want. That's your best fit. And you should extend your line to cut across the two axes. The way it's showing on this plot, this is not what you want. You will lose mark if you plot this. So you need to make sure that your straight line best fit is going through your axis. If it's passing through the origin, that's fine. But if it's not, let it cut across y axis, whether it's in the negative side or positive side, and let it cut across x axis as well. So whichever way, just by looking at the shape of your graph, you can already tell whether the slope you will get is a negative slope or a positive slope. So like I said, the positive correlation one will give you a positive slope, and we'll get slope in a bit, while the negative one will give you a negative slope. So keeping that in mind, we get to the slope. Now, how do we estimate the slope of a graph? On this plot, you can see the straight line and the blue triangle, the blue line that makes this triangle. It's so important. In fact, one of the things that people miss out, common mistakes that people make, is that for this triangle, some people make it small in estimating their slope. Now, you want your triangle to be big enough that first it should cover all your data points. It should cover all your data points from beginning to the end, even if they do not all pass through the straight line. And you want to make sure it's very clear. Use a HB pencil that is, clear on your plot, on your graph paper, and show the perpendicular line or rather perpendicular angle that is formed at the triangle edge, then label the edges. So here you have your x2 and your y2, that is the highest value of y and the highest value of x. You name it. You mustn't follow this convention. You can decide to name it or however you want to do it, but just name it. Then this will be your x2, okay, for down here x2, but here you have your y1, x1, okay, y1, x1, x2, y2. So for you to get the slope, you now have to estimate the y2 minus y1 and the x2 minus x1. But I want you to note something. This is something that you might find useful. When choosing where to draw your triangle from, you need to make sure that it's coming from one of the bold intersections, not from the tiny ones that it becomes difficult for you to read off. So you want to choose from the bold ones as opposed to from the tiny ones. So if you have, there are points here, you can actually decide to choose this point in the middle to draw your triangle, but you can imagine that will be hard to read off. So it's not like it's incorrect, but it's easier for you and it will pay you off if you go to where you have a solid line. For example, here, choose that where you have a solid line on both directions, so on both your x and your y, right? That will be easy for you, and then you can take it all the way down. The same thing for this side. Choose somewhere that you have a solid line that is easy to read off on both axes and draw your triangle from there. Okay, now this is the equation for your slope. If you are using this type of graph that we are looking at, it should give you a positive slope, so you will get a positive value. And don't forget to include the units. However, the experiment we just looked at, when you plot the graph, it's actually supposed to give you an inverted graph. So when you list out the values of your y, you will be getting something like it. Just by looking at your y values, right, you can already see that you are getting a negative. So your y2 has a small value compared to your y1. So when you subtract a small value from a big value from a small value, you know that you are getting a negative already. So that's how you get the slope. And the unit, very important. How do you get the unit from your slope? The unit is usually the unit of your y-axis divided by the unit of your x-axis. So in this case, your y-axis, remember, was second per square, right? And your x-axis is gram. So y-axis second per square, x-axis is gram. So your unit should be second per square over gram. So you see that what I've written here is incorrect. In fact, this one should be up here, right? That's the correct unit. So again, I intentionally left it this way so that you can, figure out for yourself that this is wrong. So, but there is some question that comes after the practical, which is useful, and you must answer them. If you forget or you miss your mark. So one of them says find Q, and it says that Q is equal to 0.68 over S, where S is slope. So if you put in the value of S and solve that equation, you should get minus 226.667, and the unit should be according to the equation. So this is going to be like 1 over slope, so 1 over the unit of slope. And if the slope is giving you this, so what that means is that I just inverted the unit. So this unit up here should be the unit for the Q, and this one should be the unit for the slope. Okay? All right. Now, the other thing that might come up is intercept. So for every straight line, there is slope and there is intercept. So this equation just helps to explain what I'm talking about, where M is usually your slope and Y is your Y, and B is your Y intercept. So in a typical graph, every graph has a way it's intercepting your y-axis, whether on the positive side or the negative side. So you should draw your line all the way to touch your graph, and where that line touches your graph, that's your y-intercept. So sometimes you could be asked, so you should report that value if you are asked with the unit, and in this case it should be your y unit. Your y-axis unit will be your unit. All right. So there are other questions that follows. For example, what are the precautions that you took while doing this experiment? So it's different for every experiment, and you must take note of the specifics. So even in mechanics, there are different types of mechanics experiments. So you have to take note of the specific experiment. For example, when we handled a meter rule. So when you're handling meter rule or any calibrated instrument, manually calibrated instrument, you need to take note of parallax. So a parallax error is usually an apparent measurement, it's not correct. It's something that has to do with our eyes. So you have to be careful and avoid, wrong measurement due to parallax when taking readings of meter rule in this case. There are also, other errors that you can get when wind is blowing your meter rule, which is supposed to be oscillating. So you need to make sure that the room is airtight and does not have wind that could, influence your results. Okay, that's a good precaution to state. Actually, they ask for 2, but I'm just giving you some other examples. You follow the instructions normally. You correct for 0 error. So when you start counting from 0, 1, 2, that's you correcting for 0 error. There are also 0 error associated with instruments like stopwatch. So you need to make sure that your stopwatch, actually starts from 0, and even your meter rule that it starts from 0. Sometimes, there could be mistakes or error. Maybe the meter rule has been chopped off a bit. You have to take note of those things. Now, repeated readings. I actually mentioned this. They will find out from your table, but you should also say that you took repeated readings to avoid those, systematic errors that happen also. You ensure that the mass did not touch the ground during oscillation, or maybe the ruler touching the ground. So these are some of the precautions you must take and you should write down as well. You ensure that the support was rigid. So when you are doing the oscillation, make sure that the rotor stand holding the ruler, they are on strong support so that nobody is injured, or maybe it does not affect your experiment. So these are just some of the experiment precautions I thought to highlight that are connected to this particular experiment. But like I said, it differs from experiment to experiment. So you were asked to show two, and you have your 2 marks for showing those two. Now, I wanted to take note here though is that you have to personalize the precaution because you did the experiment. So you can't just say parallax error, or just say avoid the parallax. You have to make it make sense. What parallax error due to what? So you must make a complete sentence that tells the examiner that you knew what you did. Okay? And you personalize it. There is another question about examples of simple harmonic motion. So what we just went through is a typical simple harmonic motion. So usually you will get questions that follows, and one of the ones we got this time is to state 2 examples. So I listed some of them: oscillating pendulum, vibration of the eardrum. First of all, what is a simple harmonic motion? So if you know what a simple harmonic motion is, you will know what to give us your answer here. So it's actually a periodic motion that involves a restoring force that is proportional to the extent of the oscillation. So you need to understand what is a simple harmonic motion for you to be able to answer this one. The vibration of the eardrum, the motion of a spring. You play with spring a lot, you can tell that it does move this way. Swing in the park, those of you that love to swing in the park, you can tell that oscillation motion as well. Okay, the last question that was asked is to explain center of gravity of a body. Remember, we found that for the ruler. So, but what does it really mean? So here I have said that the center of gravity of an object is defined as a point at which the whole mass or weight of that object is assumed to be concentrated, right? And it's usually like that point where the whole weight of the object lies. And that's the point where if you balance or suspend it, it will stay at equilibrium. It will not fall out. Okay? So that's what center of gravity is about. And I think that's the end of this question. And most of the points are in the nitty-gritty. So you have to take notes, make sure that they are well represented for you to get your full marks, right? Okay, I know the exam is around the corner, preparations are underway, and I wish you all the best. I hope this video was useful. If it was, then share it, let your classmates, your colleagues see it and spread the word. And subscribe to our page. If you want to reach out to me, feel free to email me or leave a comment on the YouTube, or use this form. You can use this form to reach out to me as well. Okay. And then we are also on TikTok, on Facebook. And find our handle. Join us and get to know when next we post our videos as well. All right. Take care. Thank you, everyone, and I will see you in our next video. Bye.